So the third and final gas law is sometimes known as Charles' law, and it's the link then between volume and temperature. And so the volume is directly proportional to the temperature. Oops, well done. And once again we've got stress. Temperature has got to be in Kelvin. For a fixed mass of gas at constant pressure. And once again this can be written in equation form. So we've got V over T is equal to a constant, or as it appears in the formula sheet, V1 over T1, and we'll put our kelvins in to stress that again, equals V2 over T2. The V is volume, and as usual the standard unit of volume is cubic metres, but you can use litres, millilitres, cubic centimetres, as long as you're using the same on both sides, because a multiplying factor would cancel out. But that doesn't work for temperature. It's got to be in Kelvin. So example we'll look at in class is the idea that if you let a balloon deflate quite rapidly, then you might notice that it feels cold, and we can use this law to explain that. So if we start with a balloon at room temperature, so a balloon of volume, let's say 200 cubic centimetres, and temperature 27 degrees Celsius, deflates to a volume, so it never gets quite to zero, it gets down to 20 cubic centimetres. Calculate its new temperature. So once again, V1 and T1 go together. So V1 is 200, T1 is 27 Celsius. It's quite a warm room temperature. Normal room temperatures would be about 20, but like I say, it comes up a lot, gives you a nice round number for your Kelvin temperature. And V2 is 20 cubic centimetres. And we're trying to work out T2. So I'm going to have to work across the way again. We get 200 over 300 equals 20 over T2. Cross multiply again, 200 times T2 equals 300 times 20. Which I can just calculate that bit, is 6,000. Divide both sides by 200. Oops. And we get that T2, 6,000 divided by 300, 30 Kelvin. And we can leave it at that. And it's actually not a very realistic value. The question, notice, didn't say calculate its new temperature in degrees Celsius, so there's no need to convert it and you're only risking making a careless mistake during that conversion. So unless the question specifically says, don't bother converting it back into normal temperatures. Now the three gas laws that we've looked at so far, you saw we wrote them in the constant form. So PV equals constant, P over T is constant, V over T is constant. All of these can be combined together into what's called the general gas equation, which in the formula sheet is actually written in that form. PV over T equals constant. So it just joins those three relationships that we've found together for a fixed mass of gas. So in all of the laws, we're looking at the idea you're not adding more gas or letting gas escape. You're keeping the same amount of gas. Let's say that's the way it's given in the formula sheet. Hopefully you've seen from the previous ones that we can probably adapt that to that form. Okay, now we've not seen a question yet on the general gas equation, so we're not sure what form it takes, but let's say the top one in the box is what's written in the formula sheet, but hopefully it's straightforward to see the second one. And it just allows for the possibility that more than one thing can vary at a time. So we'll do an example based on that. So let's say there's a volume of 20 cubic centimetres at standard temperature and pressure, which would mean room temperature and atmospheric pressure. So we'll take our room temperature this time to be 20 degrees Celsius, and atmospheric pressure, well actually if you look at it very precisely, it's often written as 1.1 times 10 to the 5 pascals. Although given it can change from day to day, that level of accuracy isn't really required. What pressure would it have at the temperature of 40 degrees Celsius and volume of 10 cubic centimetres. So we've doubled the Celsius temperature, but remember Celsius temperature doesn't matter, it's Kelvin temperature, so that's not going to be doubled. We've halved the volume and we're trying to work out the new pressure. So once again, just listing our variables, what we know. So P1, 1.01 times 10 to the 5. V1 is 20 cubic centimetres, so grouping all of that data that was together. T1 is 20 Celsius. And remember, I know we're doing this quite repeatedly just now, but show all your working. It's 293 Kelvin. P2 is what we're being asked. V2 is 10 cubic centimetres. T2, although it's 40 Celsius, it's the Kelvin temperature that matters. And then our formula, P1 V1 over T1, P2 V2 over T2, and then just plug in the values. 1.01 times 10 to the 5 times 20, all divided by 293, equals P2, which is what we're trying to work out, times 10, all divided by 313. How you deal with arithmetic is up to you. Probably if you're not so sure, we'll just start by cross multiplying. So 1.01 times 10 to the 5 times 20 times 313 equals P2 times 10 times 293. I'm going to do 2 steps at the one here, and I'm going to just simplify all the arithmetic that I can, but then I'm also going to swap sides. So I'm going to do the P2 times 10 times 293, and then calculating the other side there. And that will give us 6.32 times 10 to the 8. Then divide both sides by 2930. And that gives us our final answer for P2, which is 2.16 times 10 to the 5 pascals.